All right. Hi, everyone. This is Guoning Yu. I'm a PhD student from Georgia State University and supervised by Dr. Guantao Chen. And the work I'm going to talk about today was done with Dr. Chen and Yanli Hao. It is a great pleasure to talk in this lecture. So today, I'm going to talk about linear arboricity of degenerate graphs. I will generally give an introduction to this problem and briefly outline our proof. And in this problem, all we are going to care about are simple and direct finite graphs. Okay, so first, linear arboricity is a famous variation of arboricity. So if we only talk about arboricity, it is the minimum number of forests into which its edges, into which a graph's edges can be partitioned. So here is an example as shown in below. And the arboricity of K44 is 3. So I have already drawn this 3 forests with 3 colors, red, blue, and green. So and we can prove it. Actually, this is indeed the smallest number because for any forest on 8 vertices, so they must have at most 7 edges, right? But in the graph K44, we have 16 edges in total. So if you partition it with only 2 forests, the total number of the edges would be at most 14, right? So there's no way that you can find a 2 forest partition. So here 3 is indeed the arboricity of K44. And for linear arboricity, this is the minimum number of edge-destroyed linear forests. So for a graph G, we denote it by LA of G. And linear forest means every connected component in this forest is a path. So we just partition a graph with union of paths. So here is also an example. We can partition this rhombic dodecahedron into 2 linear forests, and I colored it using yellow and blue. So we can see in each color, we only have the union of paths. And of course, here we cannot find a one linear forest partition, right? So this is the 2 is the smallest number, and the linear arboricity of this graph is 2. So by these settings, we have we can have some immediate conclusions. So let G be a graph with maximum degree delta. First of all, this could be seen as a generalized edge coloring problem, because we could consider each linear forest partition with like in each linear forest, we can just let each path to be single edges. So by Wiesen's theorem, the linear forest LA of G, linear arboricity of G, is less than equal to the chromatic index of G, which is less than equal to delta plus 1. And this is a very large upper bound. And we can also see that in order to cover all edges incident to a vertex of maximum degree, we need at least the seeding of delta over 2 linear forests, right? Because for the vertex with maximum degree, a path going through this vertex will have at most 2 degrees incident to this vertex, right? So this is the seeding of delta over 2. And third, since every linear forest has at most n-1 edges, if we consider G as a delta regular graph, we can see that the linear arboricity of G must be greater than equal to the total number of edges divided the number of edges in each linear forest, right? So this is E of G over n-1, and because G is delta regular, the total number of edges is n times delta over 2. So this is greater, strictly greater than delta over 2, right? And that means for regular graphs, the lower bound of the lower bound of the linear arboricity of G is delta plus 1 over 2 seeding. And here delta over 2 seeding is for regular graphs, for normal, for like just graphs, right? So it turns out that in 1981, Akiyama, Exo, and Harari asserted the same upper bound for any graph as in the regular graphs. So here is the famous linear arboricity conjecture, and we can call it LAC for short. If G is a graph with maximum degree delta, then its linear arboricity is at most delta plus 1 over 2 seeding. So if this is true, we can see that the linear arboricity of any graph G is within a very small range, right? So it is like greater than or equal to delta over 2 seeding and less than or equal to delta plus 1 over 2 seeding. And we can see here if the maximum degree of G delta is odd, it will only have one value here, right? And if delta is even, then the linear arboricity of G is either delta over 2 seeding or delta plus 1 over 2 seeding. So it's kind of like the edge coloring problem. So so here are some previous results on the linear arboricity conjecture. First, in the original paper that LAC was posted, these 3 people proved LAC holds for some classes of special graphs. For example, complete graphs, complete bipartite graphs, and trees. And they also proved that the maximum degree is equal to 3 and 4. And later on, Adamoto and Karoshi in 1984 proved that the linear arboricity conjecture also holds for delta equal to 5, 6, and 8. And then in 1986, delta equals to 10 was proved by Guoning. So we can see for small deltas, there are still some gaps. For example, delta equals to 7, delta equals to 9, and we don't even know for delta is greater than 10. So, and in later, the LAC was also confirmed for planar graphs by Jianliang Wu in 1999 and Jianliang Wu and Yuwen Wu in 2011. And actually, they proved for planar graphs with first degree 7, and then they proved the LOC for planar graphs with all other degrees. So they have 2 papers. And people are also care about the approximate result for LAC. So for this kind of problem, we can actually consider it as a regular graph, because since every graph can be embedded into a regular graph with the maximum degree, right? So with the previous lower bound for regular graphs, the linear arboricity conjecture is equivalent to prove that the linear arboricity of a graph is equal to delta plus 1/2 seeding for the delta regular graphs. And in 1988, proved by along with probability method, the linear arboricity of graph is less than this value, delta over 2 plus big O of delta log delta over log delta. So with probability method, we can have a approximate upper bound for linear arboricity conjecture. And later it was ameliorated by Along and Spencer in 1992, and actually they improved this bound. And the most recently, Ferber, Fox, and Jean in 2019 proved that there exist constant values R and C for which the delta regular graph G its arboricity is upper bounded by delta over 2 plus C delta to the power of 2 over 3 minus R. So this is actually a very nice result to approximate the upper bound of linear arboricity conjecture. And our work is based on degenerate graphs. So we proved some result on degenerate graphs. So first, what is a degenerate graph? So for any positive integer k, graph G is k degenerate if it can be reduced to a trivial graph by successive removal of vertices of degree at most k. And equivalently, it can also be defined by every subgraph of G has a vertex of degree at most k. So we can easily think about it. Trees are one degenerate, and actually, one degenerate, like any one degenerate graph, is equivalent to forest. And outer planar graphs are 2 degenerate. Planar graphs are 5 degenerate. So here is an example. Actually, this is a 2 degenerate graph. So we can see by removal from the most from left to right. So we remove the vertices one by one, because this, for example, the most right one is has degree 2, right? So it has degree less at most 2. We can remove it, and we can remove them one by one, and then eventually we will have a trivial graph. So by this removal process, actually we get an order of a degenerate graph, right? An order of the vertices. So we actually used it in our proof. and we define this ordering. So actually every K degenerate graph admits K degenerate vertex ordering, which is that ordering like V2 to Vn of vertices of G such that the number on its left is at most K. The neighbors on its left is at most K for every vertex in this graph. So for example, here we can see each vertex has the right neighbors at most 2, right? This is a 2 degenerate graph. Here K is 2. So this is a very nice property of K degenerate graph, and we use this to prove our main theorems. So our main theorems are for any K degenerate graph G with the maximum value of G is greater than or equal to 2K squared minus K, its linear arboricity is equal to delta of G over 2 seeding. And we also consider the original upper bound in linear arboricity conjecture. So this could be the with a requirement of delta G a little bit less. So this is delta of G is greater than or equal to 2K squared minus 2K. So it has an upper bound as stated in the linear arboricity conjecture. And I'm not going to talk about the details of the proof, but I can give you an brief outline of our ideas. So first, we kind of embedded each graph, like for a given graph G, we embed it in some kind of regular graph. We define here a graph D1 regular if all its vertices are of degree either D or 1. So we can embed our graph G into a delta 1 regular graph, if delta being its maximum degree. So if G is K degenerate and it is embedded in delta 1 regular graph, so we can just think about like a ordering like before. We add vertices with like only degree 1 to those vertices, connect to those vertices that has degree less than delta. So in that way we can have a embedding of this of any graph, right, of any graph G. And if G is K degenerate, because we add all the vertices to its right hand side, so that means the graph we obtain will also be a K degenerate graph. And because G is embedded in the new graph, we call it G star, and clearly this new graph will have like the linear arboricity of the original graph is at most the linear arboricity of the new graph, right? Because G is the subgraph of G star. And so we proved, so we can restate our main theorem here. If G is a delta 1 regular K degenerate graph with the requirement, with the degree requirement delta is greater or equal to 2K squared minus K, then we can find a linear forced partition F equals to here each F sub K is the linear forest with the number of linear forest t equals to delta over 2 seeding. So actually, we can also think about this as a coloring problem, right? So each linear forest partition have a specific color. Like we can color it 1 to t, right? So our idea is related to the order of the k-degenerate ordering of this graph, because we can first delete all the vertices on the right hand side with only one vertex left, and we just add the vertices one by one in that ordering, and in that way we can keep the new vertices that's being added connect to at most delta vertices in the previous graph. So we used that property and color all the edges, and then we eventually obtain we can maintain the number of colors here, and eventually we'll get a linear forest partition with number of linear forest delta over 2 seeding. So we actually used 2 lemmas, and each lemma cares for different degree requirements by adding those edges, like by adding new vertices and new edges. So the first lemma cares about those vertices with small degree. So we can see if we can add, for example, the vertex y, and it connects to all the vertices to its left, and if the edge xy between edge xy is to be added, and if these two vertices have this degree relationship, so we can add this xy and color it by some color, and then just keep the number of linear forests. And so here, this degree requirement means those two vertices does not have much like neighbors, right? And for lemma 2, it cares about the vertices with larger degree. That means it has not only left vertices less than like at most delta, but also it has right neighbors, which is greater than d. And actually, we used this d as delta in our proof. So and this lemma gives us an system of distinct representative of all the right neighbors of the vertices. So that means we can color them by different colors, and we just add all those edges into the original linear forest partition. So by that way, we can manage to color all the edges and add all vertices back and keep this kind of linear forest partition. Okay, so that is all I wanted to see here. If you have any questions.